Okay, so this is the outline of chapter 30. Okay, so first we will introduce Faraday's law and Lenz's law. And then we will also study the induction and energy transfer, and then the induced electric field. Okay, so actually all these are included in the Faraday's law, so it's like a subtopic. And then we'll also introduce the third circuit element called the inductors. And then for the inductors, it has self-induction. And then, maybe our circuit, I will just skip it first. I will wait until after finishing chapter 27, and then I will come back to talk. And after finishing this chapter, actually I will introduce some math, okay, before move on to chapter 27. Okay, I will actually teach you how to solve the constant coefficient ODE, linear constant coefficient ODE beforehand, okay, because we will use it frequently, and actually for engineering student, you will use it later on, okay. So for magnetism, for civil engineering student, you won't use electromagnetism later on, but solving ODE, for solving linear constant coefficient ODE will be useful for all engineering students. Okay, so it is quite important, so I just supplement it after this chapter, but so I just skip this part first, and then I will talk about the energy stored in the B field and energy density in the B field. And then finally, we'll talk about the mutual inductance, okay, mutual induction. So it is like, it's actually like a transformer, okay. So, okay, so here we will talk about the Faraday's law. So here is the first experiment or the first setup. Okay, so here it says a conducting loop is conducted to a sensitive ammeter. Ammeter means a meter can measure the current. Okay, measure the current. We have a ohm meter and voltmeter. Voltmeter and ammeter. Voltmeter used for measure voltage or electric potential difference. We have voltmeter and ammeter for current. Okay, so it's connected to a sensitive ammeter. So here you can see this is the loop. Okay, it connected to, this is the ammeter. Ammeter. Okay, so because there is no battery or other source of EMF. EMF you can first consider is a battery or a voltage source. Okay, in circuit theory we generally call it a voltage source, but somehow you can consider it a battery or a potential difference. Okay, so it can generate an EMF, but actually EMF can have some other meaning. You see it in this chapter, but up to this moment you can consider EMF is just a battery or a voltage source. We generally call it a battery voltage source. Okay, so there is no current in the circuit. Okay, because there is no. So first of all, you just ignore this part first. If you only have this coil and then connect to an ammeter without a battery, then this loop won't have any current. This is easy to understand. So, but however, here if we move a bar magnet towards the loop, a current suddenly appears in the circuit. The current disappears when the magnet stops moving. So now we just pick a magnet bar and then put it closer to the loop. If your magnet bar is moving, then there will be a current. But if you stop moving the magnet bar, just place it nearby or even inside the coil. If the magnet bar stop, then the the current also disappears. Okay, so if we then move the magnet away, a current suddenly appear, but now in opposite direction. Okay， 所以中文简单说的话就是如果你没有那个磁棒的话，它就没有电流嘛，很简单。但是如果你拿一根磁棒来你靠近这个线圈，它就会突然产生电流。然后如果你靠近它，但是停下来的话，只要你不动，它就没有电流。然后你如果要把它拿开的时候，它又有电流了，但是那个电流就反方向简单来说是这样。Okay, so the next page, if we experiment for a while, we would discover the following. Okay, so a current is appear only if there is relative motion. 就是如果有一些相对运动的话有相对运动的话，就是你可以动这个 magnet bar， 也可以不动 magnet bar， 动那个动下面那个线圈跟那个电流表，或者是线圈就够了，就是动那个线圈不动 magnet bar， 或者是两个反方向动，或者是两个不同速度去动也可以。Okay, so a current appear only if there is relative motion between the loop and the magnet. The current disappear when the relative motion between them cease. 就是没有相对运动。如果两个是同一个方向、同一个速率一起运动的话，它们也没有所谓的相对运动，那也不会有电流。Okay. And then there are some more observations. So the first one is faster motion of the magnet produce a greater current. 就是动得快一点，电流就会大。Okay, if moving the magnet north pole towards the loop cause, say, clockwise current, then moving the north pole away cause a counter-clockwise current. 就是如果都是用北极的话如果靠近它会顺时钟的电流移走它的话就会逆时钟，或者是moving the south pole towards away from the loop causing current but reverse direction from the north pole effect. 就是如果现在本来是北极的，我拿南极的话，就会跟北极的电流方向刚好相反所以目前有一些观察Okay, so for the third page, we try to adjust this experimental setup. Okay, so this is the second experiment. Okay, for this experiment, we use the apparatus. Okay, so the 装置或者是仪器 Okay, apparatus with two conducting loops close to each other, but not touching. 就是现在我们拿两个线圈因为上一章的时候我们学嘛，就是线圈就是 magnetic dipole 嘛，那这个 magnet bar 就是 magnetic dipole 嘛，那所以的话我们就把它换成这个，但是 magnetic dipole 是什么嘛 ？NIA 嘛 ，mu 等于 NIA， mu 等于 NIA， 所以要有个圈有面积有圈数但至少一圈嘛。那要有电流所以我们改了这里。Okay, so if we close switch S to turn on a current in the right hand loop, the meter suddenly and briefly register a current and induce a current in the left hand loop. Okay, so for this loop, we of course have this current loop here. And then we have a resistor, we have a battery, we also have a switch. Okay, so the setup here is the objective is that we don't need to move the loop. Okay, so for the previous experiment we need to move the magnet bar, we need to have relative motion, but here what it wants to have is we try to avoid any movement. Okay, we just need to switch it. So this kind of current does not necessarily need relative motion, but for this one we need because this magnet bar we cannot change the magnetic dipole pattern. Okay, so we we need to change the B field by moving it. Okay, so here, if we have a switch here, we can change the B field generated by this coil, so we don't need to physically move it. Okay, if the switch remains closed, no further current is observed. If then open the switch, another sudden brief induced current appears in the left-hand loop, but in the opposite direction. Okay, so all these two paragraphs， 就是这两段的话，就是告诉你说，如果我一开始是这个 switch 是打开的，然后我们把它闭合之后，突然间就会有一个 current， 然后就会消失，然后再来的话，你再把它打开，你再把它开路的话，又有一个电流出现，但是反方向的。Okay, so the phenomenon we observe is similar to previous one, but at this time we don't need to physically move the second coil. We only need to switch it on and off. Okay, so we get an induced current only when the current in the right-hand loop is changing. Okay, so it's changing. Changing is the invariant. 就是物理啊，或者是有一些数学的话，就是找一些不变的东西，可以应用在不同的地方。就是这两个场景里面，就是这个在动，这个就没有动。但是他们两个共通的就是我们改变了一些东西，改变了什么？后面就会告诉你说是改变了 B field 就是 the loop is changing, either turning on or off, and not when it is constant， 就是只要它不动，第一个圈就没有电流。Okay, the induced EMF and induced current in this experiment are apparently caused when something changes. But what is that something? Faraday's new. Okay, so here Faraday realized that an EMF and a current. 你可以把它理解成一个中文叫做电动势的 electromotive force， 中文叫做电动势电动势，你可以理解成它是一个potential difference 的感觉，但是它又不是那样，它是围绕着那个线圈有一个 potential difference， 让它有一个电流讲起来很玄的感觉，但是不好解释这个，就是它你可以想象，简单的来说，你可以把它想象成一个 potential difference， 让它有一个 current，and can be induced in a loop. In our two experiments, by changing the amount of B field passing through the loop. So he said, actually the B field passing through the loop is changing. This change induced the current. Okay, so he further realized that the amount of B field can be visualized in terms of B field lines passing through the loop. The magnetic flux through an area A in a B field is defined as this one. Okay, so similar to electric flux. When we learn Gauss law in chapter 23, we have similar formula like this. Phi E equals integration of E dot dA. Okay, so just for a open surface, not a closed surface. If it is a closed surface, we have a circle here, but here we don't have a closed surface because the surface is enclosed by this coil. So this is sure an open surface, So phi B will be integration of B dot dA, similar to this one. So where the integral is taken over the area, the SI unit of magnetic flux is Weber. Weber. Okay, sorry. Weber. For this one. this is actually T times meter square of Tesla. So B is Tesla, area is meter square, so T meter square is actually Weber. Okay, if B is perpendicular to the area and uniform over it, then this integration becomes a product, just as what we have before. Okay, so this is why I emphasize that B field is not magnetic field. B field is magnetic flux density. Here you can, from this you can follow this formula, you can get the idea. Yeah, because if you just integrate the B field over the area, it becomes the magnetic flux. So B should be magnetic flux density rather than magnetic field. Magnetic field should be H field. Of course, in this textbook, it didn't mention the H field in the textbook for simplicity. But yeah, so I emphasize this the magnetic field mentioned in this textbook should be called B field. Should be called B field or magnetic flux density. Okay, so here here's a highlight. It says the magnitude of the EMF induced in a conducting loop is equal to the rate at which the magnetic flux through that loop changes with time. Okay, so this is actually the Faraday's law itself. The Faraday's law itself. Okay, so if we need to write this statement into a formula, it would be like this. E. Okay, so this E is this E. I cannot find the find the font in the PowerPoint, so I just use this E here. E equals negative d phi b dt. D phi b dt. So writing this statement in a formula will look like this. Okay, so this is the derivative of the magnetic flux with respect to time, and then take the minus sign. We will EMF. We will induce EMF. Induce 就是中文叫做感应嘛，感应就是感应电动势嘛，或者是感应电流 ，induce current 就是感应电流。Okay, so for coil of n turns, if we have n turns rather than a single turn, then E equals negative n d phi b dt. Okay, so nothing special here. Okay, so and the minus sign indicates the opposition. This minus sign is referred to Lenz's law. Just as what I mentioned in Faraday's law, this minus sign already called the Lenz's law. Already called the Lenz's law. 那你觉得很奇怪，这个已经叫法拉第定律，那这个负号又叫 Lenz's law。那你可以猜测的话，就是当时他应该先发现这个 Lenz's law 那后来的话，他就把它写成一个式子，所以这个整个式子就叫 Faraday's law。那有了 Faraday's law， 你也不能把它抹杀掉啊，所以它还是叫做 Lenz's law 大概是这种故事吧Okay, so yeah, okay, so before talking about the Lenz's law, we have a sample problem first. But maybe let's have a 10 minutes break and then